Today in the workshop we'll be interfacing high current devices with an Arduino. I'll show you how to use BJTs and MOSFETs to control a lamp, a motor, and an RGB LED strip. We're taking control today, so welcome to the workshop. Hello and welcome to the workshop, and today we're going to be working with one of the basic building blocks of electronics, and that would be the transistor. Now the transistor is the heart of everything electronics these days. The chips that are inside your cell phone, the chips that are inside the Arduino itself, in your computer, your television, all of these rely on transistors. The invention of the transistor in the late 1940s at the Bell Telephone Labs in New Jersey is, in my opinion, the greatest invention of the 20th century, because everything, the advances we made in medical research, in telecommunications, in entertainment, in space exploration, then none of those would have been possible without the invention of the transistor. And so what can this wonderful device do for us today? Well, it can help us with an issue we have with Arduinos and Raspberry Pis and all sorts of microcontrollers and microcomputers. Microcontrollers and microcomputers are wonderful things to build automated systems out of, and we've been doing it for a while, but what they cannot do is they cannot drive a high current load directly. Now we've already seen this when we've worked with things like stepper motors and DC motors. We've used driver boards, and those driver boards have transistors on them that take the low current signal from the Arduino or Raspberry Pi and use it to drive a high current signal. Now today we're going to be working with two specific types of transistors: bipolar junction transistors, which are commonly called BJTs or just regular transistors, and also metal oxide semiconductor field effect transistors, which are called MOSFETs. And we're going to use these with the Arduino to drive loads that the Arduino would not be capable of driving itself. Now I should mention this is not the only way to interface things to the Arduino, and today we're going to be concentrating on DC voltage loads, not AC. In order to use AC, there are different techniques, and I will be covering that in a future video, but today we're going to be driving DC loads with transistors. So let's start off by learning a bit about transistors. Let's take a look at bipolar junction transistors and MOSFETs. The first transistor was developed at the Bell Laboratories in Murray Hill, New Jersey in 1947 and was patented in 1948. The 1956 Nobel Prize was awarded to John Bardeen, Walter Brattain, and William Shockley for the discovery of the transistor effect. Transistors quickly replaced vacuum tubes in electronic devices. Integrated circuits like microprocessors and microcontrollers use transistors. Transistors can be used for many things. They're primarily used as amplifiers or switches. We'll be interested in their use as switches today. A BJT is a bipolar junction transistor. Sometimes it's called a bipolar transistor or simply a transistor. There are two main types of bipolar junction transistors, the NPN and the PNP. These transistors have three leads: the base, the emitter, and the collector. Here's a circuit with an NPN transistor, which is the type that you'll encounter the most often. You'll notice that we have a low current source and then a high current and high voltage source that is driving a load on the other side of the transistor. We'll apply a low current to the base of the transistor. This will switch the transistor on, allowing a high current to flow through the collector and emitter. In a sense, when the transistor is on, it behaves a lot like a diode. A MOSFET is a metal oxide semiconductor field effect transistor. There are two main types of MOSFETs, the N-channel and the P-channel. MOSFETs also have three leads: the gate, the drain and the source. Here's a circuit using an N-channel MOSFET, which is the type that you'll encounter the most often. Notice this time that we have a low voltage source, as well as the same high voltage and current source with a high current load on the other side of the MOSFET. When we apply a low voltage to the gate of the MOSFET, it turns on. It then displays a very low resistance between the drain and the source. In a sense, you can think of a MOSFET as being a switchable low-value resistor. BJTs and MOSFETs are available in many case styles. The pinouts differ between devices, so make sure to check your spec sheets before wiring yours in. Power devices require heat sinks in order to achieve their rated maximums, so make certain to provide adequate heat sinking. Bear in mind that power devices have one lead connected to the case. You'll need to know that, especially if your heat sink is going to be connected to ground. Now let's take a look at a few transistors that I have in my parts drawers. So I've opened up a few of my parts drawers and brought a few transistors down just for you to look at. Now this is a combination of different NPN and PNP bipolar transistors, some FETs, some JFETs, a number of different types of devices. Most of them are fairly common ones. What I wanted to show you was the different packages you could get transistors in. Now these packages have names. I'm going to kind of go by memory, so hopefully I won't get these wrong. But I believe these are what are called TO92 packages over here, and let's see if you can see one of these over here. You'll notice it's got a flat side. I'm hoping you can see that, and a rounded side, and that's how you identify the two sides. The writing is on the flat side, and then you'll have to look at the spec sheet to see which is the base, emitter, and collector, because there is no standard between transistors for that. So you can find two transistors in the same package with a different pinout. These two particular ones over here, these are 2N2904s, and these are 2N3904s and 3906s. What's interesting about these two is, first of all, they're two of the most common transistors that you're going to find anywhere. They've been around for decades. And secondly, these are what they call complementary pairs. These are NPN and these are PNP, but they have basically the same specifications otherwise. And you'll find complementary pairs are used a lot in analog circuits such as audio amplifiers and oscillators, where they need both a negative and positive side, and they'll use both NPN and PNP transistors. So all of these are in TO92 type packages. This big package over here, this is what I believe they call a TO66 or a TO3. I think it has two different names. And in this kind of package, you'll only see two leads, and you'll see that the case is connected, I believe, usually to the collector of the transistor. And that's one thing to note, is that these are obviously power transistors from the size they are. And when you bolt something like this down to a heat sink, which you're going to want to do to get the maximum performance, you have to remember that one side is actually connected to one of the leads. In fact, that's how you connect to it. So if your heat sink is grounded, you could end up shorting something out depending on your circuit design. And usually we use things like mica insulators to connect them onto heat sinks while insulating them electrically. The mica insulator will allow the heat to transfer. There's other materials other than mica that they use nowadays. I'm kind of old school as far as that goes. This is a very common package for a power transistor. It's called a TO220. In fact, the ones that we're going to use today, which are the ones over here, are in a TO220 package. And again, the heatsink side of the package will be connected to one of the leads of the transistor. And so once again, when you mount this, you have to make certain to either isolate your heatsink from anything else or to use some form of an insulator. You have to be very careful if you're using a number of these transistors and you want to put them all onto the same heatsink. Again, you have to remember this is electrically connected to part of the transistors. But this is just sort of an assortment for you of the different packages that you can get transistors and MOSFETs in. Now here's a look at the transistor that we are going to be using today, the TIP120. It's in a TO220 package, and so it basically has a tab on the top over here that you can mount to a heatsink. Now electrically the tab is connected to the center lead, so keep that in mind when you're placing your heatsink. Make certain that you don't ground the heatsink or that you use an insulator between the heatsink and the transistor. The pinouts of it are as follows. This pin over here on this side, on the left side, is the base. The center pin is the collector. Again, that's the one connected to the tab. And the emitter is the third pin over here. And this is the transistor we'll be using in our experiments. Let's take a quick look at the spec sheet for that transistor now. Now here's the specification sheet for the TIP120, and as you can see by scrolling down, there's a lot of information here. Some of it you'll need to know, some of it you can probably ignore, especially for the purposes that we're going to be using the transistor for. An interesting thing about this transistor is it's a Darlington transistor, and a Darlington transistor actually has two bipolar transistors in the same package. The first one provides additional gain and improved current capabilities, and so this is a high gain transistor. Now you'll notice it says it has a complementary transistor. If you recall from when we looked at the transistors earlier, that means that there would be a PNP transistor that would be the electrical equivalent of this one, and you would use that in something like an audio amplifier output where you needed both an NPN and PNP. Rather than go through all the specifications here, I will just show you some of the key ones that you will need to know. The current gain is something that you might want to know, and it's typically about 1000. The collector emitter voltage and collector base voltage are 60 volts, and so that's going to be well within the range of what we're going to be using. The continuous collector current is 5 amperes, and the peak load is 8 amperes, and that of course is an important spec when you're hooking it up to other devices. Another thing to know is that the base current is a maximum of 120 milliamperes, which should be no problem for us, and that allows you to select a resistor that you're going to be using on the base, because remember that bipolar transistors are current driven as opposed to MOSFETs, which are voltage driven. And so you'll find a spec sheet for pretty well every transistor there is out there, and so if you need to do any transistor substitutions, you can take the spec sheet of the one that you're trying to substitute and compare it to the original one and see how they match up, and that way you can select another transistor if you don't happen to be able to get this particular one, although the TIP120 is one of the more common transistors. Now this is the MOSFET that we're going to be using in our experiment today. This is a very popular MOSFET. It's an N-channel power MOSFET. It's an IRF520, and you can see it here in a TO220 package. And in this package, the pinout is as follows. It's got the gate on this side, on the far left side, the drain in the center, and the source on the right side. Now you can also get this IRF520 as part of a very popular module, and I've got one of these modules here as well. The module just makes it simpler to wire up to the Arduino and to wire to a high voltage, high current load and power supply on this side. And I'm going to use some of these modules in my design today, but if you don't have the modules, you can just use the TO220 package IRF520. You'll need an extra resistor that's already included on the module. Now let's take a look at the spec sheet for the IRF520. Here's the specification sheet for the IRF520 MOSFET. Now this is the MOSFET that is on the module that I'm going to be using, but if you're not using a module and you want to use a discrete MOSFET, this will come in handy. Now one of the handiest things it's going to show you is the pinout. You've got the gate, the drain, and the source, and they're illustrated over here in the TO220 package. Keep in mind that the drain is also connected to the tab of the package, and so as you can see from the circuit, if you were to ground that, you probably would have serious problems, and so bear that in mind if you're adding a heatsink to your device. Otherwise, it's similar to the last spec sheet in that it has a lot of specifications, some of them that you probably just don't need to know, some of them which are actually quite useful. I'll go over once again the primary specifications of this. It's an N-channel power MOSFET. It has a continuous drain current of 9.2 amperes, and so that's quite a bit of current that this thing can handle. Now keep in mind, these ratings always assume that you have heat sinked the device. Drain to source breakdown voltage, so between here and here, the drain and the source, you've got a breakdown voltage of 100 volts, so it isn't going to handle more than 100 volts, and you'd be wise to keep it much, much lower than that. The drain to source resistance is 0.27 ohms, and so when this thing is on, it's only going to offer 0.27 ohms of resistance, and that's why the MOSFET is so efficient, and why it will dissipate far less heat than the equivalent bipolar transistor when dissipating the same load. Okay, the gate threshold voltage is 4 volts maximum, and that's a very important specification when you're trying to use this with logic circuits. Now, this is not necessarily the best MOSFET to use with logic circuits, but it'll work with a 5-volt Arduino, because with 4 volts maximum, it means you need at least 4 volts into the gate to turn this on. However, if you're using a 3.2 volt Arduino or a Raspberry Pi, it may not be sufficient, and there are other MOSFETs that would be more suited to the job. Another thing is the rise and fall time of 30 nanoseconds and 20 nanoseconds. If you're pulsing things, or if you were to use this as part of an audio amplifier, that would be an important specification. And so there you go, the specs for the power MOSFET that is on the module that we're going to be using, the IRF520. Alright, now we're finally ready to start with our experiments, and for the first one we are going to be using the transistor I just showed you, the TIP120 Power Darlington, and we're going to be using it in order to drive this. Now this is just a 6-volt lantern, and it uses an incandescent bulb, so it takes a reasonable amount of current. You could not drive this directly from your Arduino, and so we're going to connect the transistor up to the Arduino and simply create an on-off switch. Now technically we don't really need to have an Arduino for this, but this is really more just to illustrate how you would connect the transistor to the Arduino to drive a simple load. So let's go and take a look at that. For our first experiment, I'll be using a TIP120 power transistor. You can use an equivalent transistor if you'd like. I'm also using an Arduino Uno, a 6-volt incandescent light bulb, and a 6-volt battery as my power source. You can use a different load and power source if you wish. Don't exceed 40 volts though. I also have a push-button switch, a 10K resistor, and a 2.2K resistor. I'll start by connecting pin 9 of the Arduino to the base of the TIP120 transistor through the 2.2K resistor. We then connect the Arduino's ground to the emitter of the transistor. We also connect the negative side of the battery to the ground of the Arduino. We connect the positive side of the battery to one side of our resistive load. The other side of our load goes to the collector of the transistor. Pin 3 of the Arduino is connected to one side of the push-button switch. That same side of the switch is also connected to the 10K resistor, whose other side is connected to 5 volts. The 10K resistor is a pull-up resistor. Finally, the other side of the switch is connected to ground. And this completes our wiring. Now here's the sketch that we're going to be using with our transistor switch demonstration, and it's a very, very simple sketch. We start off by defining out pin, which is the output pin on pin 9. This is the one that connects to the 2.2K resistor and then to the base of the transistor. Then the button pin, the pin from the push button, is on pin 3, and this is the pin that's being held high with the 10K resistor. We also define an integer called button val, and that just holds the value of the push button. And then we go into the setup, and we'll set up the out pin as an output and the button pin as an input, and we'll also do a digital write to the output and set it low just to make certain that the transistor is off when we go into the loop. Now we go into the loop, and the first thing we do is we read the push button value with a digital read on the button pin, and we assign that to the button value. Now that's either going to be high or low. Now remember, it normally will be high if nothing's happening to the push button, because the resistor will be pulling it high. So if the button value is high, the button hasn't been pressed, we just make certain we're still writing a low to the transistor, and then we delay by 20 milliseconds as a form of debouncing, and we go and do it again. However, if the button value is low, then the button has been pressed, and what we're going to do is turn our lamp on for 5 seconds. So we'll do a digital write to the output pin, and we'll send it high, which should turn on the transistor because it'll let current flow through that resistor. And then we'll delay that by 5 seconds, and then we'll turn it low to turn everything off, and then we'll go back and do the loop over again. So again, a very simple sketch. Let's go and take a look at it now. Alright, here's our experiment number 1 all set up. Now this is our 6-volt lamp and the 6-volt battery that's driving the lamp. Of course, we've got our Arduino over here, and on the solderless breadboard, if you can see it at the back here, we have our TIP120 power transistor, the power Darlington. Down in front of it is the 2.2K current limiting resistor, and over here I've got my push button and the 10K pull-up resistor, and on this breadboard I've got the red rail over here tied to the 5 volts of the Arduino and the blue one tied to ground. Now this yellow wire is the one that goes to pin 9 of the Arduino to control the transistor. I'm going to remove it from the Arduino for a moment. I'm going to tie it up to the positive rail. And as you can see, our light is lighting because I've allowed current to flow through the current limiting resistor into the base of the transistor, and it has turned it on and has allowed the current to flow to light the light up. Now, one thing I want you to notice is how bright the light is right now. I'm going to disconnect it from the transistor for a moment, and I'm going to just put it back on the negative rail. As you can see, that's a lot brighter, and the reason for the difference is the voltage drop, the 0.7 of a volt that we're getting through this transistor. That's enough to cause a notable difference in the brightness of the light, so it's one reason why bipolar transistors aren't necessarily the best. I'm going to just put that back, and that should be my light. Okay, let's put that back on pin 9. I'll just reset my Arduino, and we'll try it out. We'll press the button, and as you can see, the light goes on. Now it should stay on for 5 seconds, and it's off. Try it again. And there it goes. And so we have a time delay light switch that we've created, which is admittedly a very simple application, but now, as you can see, you can control this lamp, this 6-volt lamp, with an Arduino. So you could really use the Arduino to write any kind of sketch to do basically anything to control this lamp. So it's a very useful technique to know. Now, as you can see, that was a very simple circuit, and it did the trick. It was able to turn on and off the light when we wanted to. But the light we are using is what we would call a simple basic resistive load. However, there are other types of DC loads that you might want to drive, and one of them is this. This is a small motor. Now, the difference with a motor and a solenoid and some other devices is they are inductive loads. They have a coil inside them, or several coils inside them. And what happens when you power an inductive load up is that a reverse or back EMF is created. This is a voltage of the opposite polarity. And when you first apply power, this voltage appears on the circuit very briefly. However, it is there long enough to potentially destroy your transistor. And so you need to do something about that. Now, the most common way of handling an inductive load is to use a diode in order to absorb that reverse EMF, and that's exactly what we're going to be doing. So we're going to hook this motor up to an Arduino. We're going to also hook a potentiometer up to it so that we can control the motor speed, and we're going to have a diode in our circuit to absorb the reverse EMF. So let's go take a look at that right now. So here's the hookup for our next experiment. As with the previous experiment, we'll start with a TIP120 power Darlington transistor and an Arduino Uno. We'll also be using a small 6-volt DC motor. You can use a 12-volt motor if you wish. I have a power supply for my 6-volt DC motor. Again, you can change that to 12 volts if you need to. I also have a diode. I used a 1N4004, which is a common rectifier diode. You'll need a 2.2K resistor and a potentiometer. I used a 10K linear pot, but any value from 5K above will work. We'll start by connecting the ground from our Arduino to the emitter of the TIP120. We'll also connect the negative side of our battery to the ground of the Arduino. We'll connect pin 9 of the Arduino to the base of the TIP120 through the 2.2K current limiting resistor. We'll connect the positive of the 6-volt power source to one side of the motor and to the cathode of the diode. Note that the cathode is the side with the stripe on it. It is very important that you get this oriented correctly. We'll connect the other side of the diode and the motor to the collector of the transistor. And finally, we'll connect the potentiometer. We'll connect one side to 5 volts, the other side to ground, and the wiper of the pot to analog input A0. And this completes our wiring. Now this is a sketch that we're going to be using to control our motor, and as you'll see, it's a very simple sketch as well. We're going to start off by defining out pin as being pin 9, and that's the pin that connects to the transistor through the 2.2K current limiting resistor. We also define pot in as being A0, that's the input from the potentiometer, and speed val, this holds the value of the speed that we're going to be passing back to the transistor to control the speed of the motor. Now in our setup, we set up out pin as being an output using a pin mode command, and we go into our loop. Now in the loop, speed val is assigned the value of an analog read of the pot in. Now that's the pin A0, and so that value is going to give us a value of 0 to 1023 because of the 10-bit analog to digital converter in the Arduino. We'll use a map command to get that down to a value of 0 to 255, and then we'll just write that out to the transistor with an analog write command, which will give pulse width modulation to the output pin at the speed value. We'll add a small delay and then start the loop again. So a very simple sketch. Let's go see it control our motor. And so here's our motor control demo ready to go. Now, of course, I've got my battery back over here powering the motor, and I've got a small DC gear motor attached to this wheel, and we're going to spin it around. Here's my potentiometer, my Arduino, of course, and then back here, my TIP120, and here is my diode, my 1N4004 rectifier diode. Now, it's very important, again, to make certain that the line, which is the cathode, is connected to the positive side. Now, that may seem backwards to you, but that's actually the reason it's there. It's to take any of the reverse voltage that comes off of this motor when the motor spins and to absorb it. And so that's why the diode seems to be connected backwards here. But you have to get the polarity of that correct. If you don't get that correct, that's going to get very, very hot very quickly. Otherwise, the resistor over here, my current limiting resistor, and then of course the line out to pin 9 of my Arduino, and you saw the potentiometer, it's just connected to the ground and 5 volts in the Arduino and to the analog A0 input. So a pretty simple circuit and a very simple sketch, and let's just watch it work. And that's full speed right now. If I can bring the speed down. Get it to a low speed. And so it seems to work quite well. We're controlling the motor with pulse width modulation sent out to the base of the transistor. And once again, the motor is something that uses current and voltage the Arduino couldn't handle directly. So you could use this technique with bigger motors, with bigger transistors, And other than just having a simple potentiometer, of course, this could all be part of a simple robot circuit. Now, we don't have any method here of reversing the motor. That would require an H-bridge. Actually, this is 1/4 of an H-bridge right here. You could build an H-bridge out of transistors if you wanted to, although usually it's a lot easier just to use a commercial one. But there you have it, controlling a motor with a transistor and a diode to absorb the back-EMF. Alright, now that we've worked with bipolar transistors, it's time to move on to MOSFETs. Now I'm going to be using those little modules that I showed you, but you could use the discrete MOSFET as well. The modules have an IRF 520 MOSFET on them, and you could pretty well use any power MOSFET that has a logic level input. Now not all of them accept logic level inputs on a gate, so make sure that the one that you pick does. Now these are very easy to hook up because, as you recall, MOSFETs are voltage driven and not current driven, so you literally just connect them right up to the Arduino. Now we're going to be needing 3 of these for this project, and that's one of the reasons I chose the module, just to simplify the wiring a bit, because what we're going to be doing is driving an LED strip light, an RGB one. Now this is a conventional LED strip light as opposed to the programmable or addressable ones, and so we basically have a red, green, and blue line, and they require 12 volts on each to drive the LEDs, and a fair amount of current because this is a 5-meter long strip light. And so we're going to use the MOSFETs to drive each of the sections. We're also going to add a few potentiometers onto our circuit so we can control the brightness of the red, green, and blue. So let's go and take a look at that right now. Now here's how we're going to hook up our MOSFET experiment. Now I'm going to be making use of very commonly available MOSFET modules, which have the pinouts that you see illustrated here. However, if you wish, you can use a discrete MOSFET instead. Here's the equivalent wiring of the module. A couple of things to note. First of all, the MOSFET is an IRF 520, which is a very common MOSFET. Second, you'll note that the VCC is not actually connected to anything, and so you don't need to use it when using the module either. Now we'll notice that the signal input is connected to the gate of the MOSFET. It's also connected to one side of a 1K resistor which goes to ground. Now on the module there's an additional 1K resistor with an LED going to ground. I'm not showing that over here. The 2 grounds are connected together and are also connected to the source lead on the IRF 520. The drain of the MOSFET is connected to the V- output terminal. The V-in and V+ terminals are connected together. And so you can use this circuit instead of the modules if you wish. Now I'm going to be using 3 of the modules. I'll also need a 12-volt power supply with sufficient current for my RGB LED strip. And of course I'll have an Arduino Uno. I'll need 3 potentiometers. I use 10K linear taper pots, and one is for red, one is for green, and one is for blue. We'll start by connecting the ground from the Arduino to one side of each of the potentiometers. We'll also connect that same ground to the ground terminal on the MOSFET modules. We'll connect the 5 volts in the Arduino to the other side of the potentiometers. We'll connect the wiper of the red potentiometer to analog input A0, from the green pot to input A1, and from the blue potentiometer to analog input A2. Digital output pin 3 will be connected to the signal input on one of the MOSFETs. Pin 5 will be connected to the signal input on the second MOSFET, and pin 6 to the third MOSFET. We'll take the negative side of our power supply and connect it to the ground pins on the MOSFETs. The positive output of the 12-volt power supply will be connected to the common positive on the RGB LED strips. We'll also connect it to the V-in pin on all three modules. The V- pin on the first module will be connected to the red connection on the RGB strip. V- on the second module to the green connection on the RGB LED strip, and the V- on the third module to the blue connection on the LED strip. And this completes our wiring. Now this is the sketch that we'll be using to drive our LED strip, and it's a very simple sketch. As you'll see, it requires no external libraries. Now first we define the output pins that we've connected to the gate of the MOSFETs, and those are these three pins, which we're going to call red pin, green pin, and blue pin. Now if you wish to use different pins, keep in mind that you'll need to use pins that are capable of pulse width modulation. Pins 3, 5, and 6 are capable of PWM, and the Arduino has 3 additional pins that are also capable of PWM, that is if you're using an Arduino Uno. Then we define the inputs for the potentiometers on analogs pin A0, 1, and 2, so that's red control, green control, and blue control. Then the variables that will hold the values that we get from the pots and then send out to the PWM, and we're going to call them red val, green val, and blue val. Now in this setup, we'll set up those MOSFET pins as outputs, so we use pin mode commands to do that. We're also setting up a serial monitor, and the serial monitor is optional, but it's just a troubleshooting tool in case something goes wrong. You can see what values we are sending out to the MOSFETs. Then into the loop. Now in the loop we do an analog read of each of the controls and assign it to their respective values. So for example, the red val is an analog read of the red control, and the other two are the same for their respective controls. Then we map those to a range of 0 to 255. Remember that the potentiometers are going to give us values of 0 to 1023 because of the 10-bit analog to digital converter in the Arduino, and we need to set that to 0 to 255 for pulse width modulation, so we just do that with a map command. And then we write the PWM out to the pins with analog write commands, and then we'll write everything out to our serial monitor so we can see what values we are sending out to the pins. And then after adding a slight delay, we repeat the loop over and over and over. So again, a very, very simple sketch. So let's go take a look at it in action now. And here is our demonstration in all of its glory. Now I've got my LED strip light over here, as you can plainly see. Most of it is still coiled up here. This is a 5-meter long strip. For those of you who don't understand the metric system, that's about 16 feet. You can see the modules I've got over here on my breadboard, the 3 potentiometers, and of course my Arduino Uno. And if you look at the serial monitor, you can observe the values on the pots as I turn them. And you can, of course, watch the LEDs as they change color as I apply different amounts of red, green, and blue to them. And really, it's a very simple display, but it's one that you can watch for a long time because of all the wonderful colors that you can get out of the LED strip. Now, one thing I noticed is I have been fiddling around with this, and I have placed my finger on a couple of the MOSFETs, and there's really no appreciable heat on these at all. In fact, there's more heat on the actual coil of LEDs over here than there is on the MOSFETs. So this just demonstrates also the efficiency of the MOSFETs, because it does take a fair amount of current at 12 volts in order to drive all of these LEDs at full blast, and yet the MOSFETs stay very cool during it. So all in all, I think a very successful and entertaining demonstration. So this brings us to the conclusion of today's video. I hope that you enjoyed it and that you now know how to hook up high current DC devices to your microcontroller. Now, as I mentioned at the beginning of the video, hooking up AC devices is a bit of a different story. It requires different techniques. The things I showed you today are only for DC, but I will be doing a video on hooking up AC devices very soon. And the best way to find out about that video, if you haven't already already, is to be subscribed to the YouTube channel. And that way, if you subscribe and hit the little bell notification, you'll get notified when that video is created. If you haven't subscribed already, just hit the subscribe button below the video or click on the little robot in the corner and he'll do the job for you. If you need some more information about transistors, you'll find an accompanying article on the DronebotWorkshop.com website, and there's a link to that article right below this video. While you're on the website, if you haven't already, please subscribe to the newsletter. Yes, there's a lot of subscribing to do, but the newsletter is my way of keeping in touch with you. It's not a sales letter. It's just my way of letting you know what's going on in the workshop. And if you want to discuss MOSFETs or transistors or anything else electronic, a great place to be doing that is in the DroneBot Workshop forums, and you'll find a link to the forum below the video as well, and you'll find all sorts of wonderful, intelligent people on the forum who'd be happy to discuss just about anything electronic with you. So head over to the forum and get in on the conversation. And so until next time, please take care of yourselves, and I hope to see you again very soon here in the DroneBot Workshop. Goodbye for now.